I really value the fact that the present weapons program no longer tests weapons in Nevada. For us, that's incredibly important. Please, let's not test. The shot on December 5 was a demonstration that the science-based Stockpile Stewardship program actually is real, that it works. And therefore, more than anything else, it demonstrates that the decision to not test and then rely on science to basically do the work that was done by testing in Nevada, that one actually worked out. We know how to do this.
Welcome to My Nuclear Life. I'm Shelly. In December of 2022, the world was abuzz with news that controlled fusion was achieved on Earth. Many of the headlines reported it as a major breakthrough in technology which would lead to an abundance of clean energy through nuclear fusion power plants. Yes, I'm talking about the announcement from the National Ignition Facility, or NIF. But was this announcement a major breakthrough for power or for something else? So today, Dr. Bob Rosner agreed to help us untangle the announcement and what it actually means. I asked today's guest to be on the podcast after reading an interview he gave for the Bulletin of the Atomic Scientist, which we referred to a couple of times, and I will link in the show notes. Bob Rosner is an astrophysicist and founding director of the Energy Policy Institute at the University of Chicago. His research has focused on fluid dynamics and plasma physics, but that does not give the full breadth of his career or his influence. Bob has served on the External Advisory Committee for NIF, was the director of Argonne National Laboratory from 2005 to 2009, and is currently the president of our scientific association, the American Physical Society. Before we begin, I would like to take a moment to thank you, my listeners. I am always delighted when you send me an email or leave us a review, and once in a while I arrive at my office to find an anonymous gift. Since I can't thank you individually, I wanted to take a moment to thank you here. It really keeps me going to know that you are enjoying this podcast. How are you related to NIF and how are you related to Livermore?
So first of all, what am I? I'm a physicist. I'm a theoretical physicist.
Okay.
I'm on the faculty at the University of Chicago in both the physics department and the astronomy department. And my excuse for that is that I'm also an astrophysicist. And I worked with folks from Livermore on a project that was related to the science-based Stockpile Stewardship program, which you probably know something about, starting in 97. I was one of the principal investigators of one of the academic alliance programs that was supported under the Stockpile Stewardship program. I ran one of the centers, the 5 centers at Chicago, and it was on blowing up stars. So you can imagine there is some relationship there to what they're doing. So I consulted with folks at Livermore and actually also at Los Alamos for a number of years. I was on the Science Advisory Committee for NIF, and once that disappeared, it was replaced by the MAC, the management group for NIF, external management group. And I served on that until I think it ended about 2 years ago.
Okay. So when was NIF first conceived and the planning started for building NIF, the National Ignition Facility?
It probably dates back to probably the 1980s.
Oh, wow. Okay.
Yeah, a long time. Because so Livermore had a long-standing laser program using lasers to do all sorts of interesting things, in particular to do compression experiments. And there were predecessors to NIF, Jupiter, for example. And interestingly enough, the folks that worked on these projects were a combination of plasma physicists, astrophysicists, and laser people. I'm guessing that no other program in the United States ever put as much money into laser research as did the program that ended up with NIF, by far.
And why did they put so much money into something like NIF?
It all had to do with the realization at the weapons labs, the design labs in particular, that the era of testing weapons in Nevada, pulling things out of the stockpile, bringing them to Nevada, burying them, and then blowing them up, that era was ending. And those tests had a purpose. They weren't just a bunch of kids blowing things up for fun.
Though it is fun.
Although it sometimes felt like that. It did feel. I had a lot of sympathies for that. But that's not the reason they did it. As you undoubtedly know, they were interested in answering a very important question, which is the weapons as designed and built age, components age. And what you don't know from first principles is how they age. We wish we did, but we don't. And so at the time, the way that you would check things is you would bring selected weapons, say pull them out basically at random, and blow them up. And the two questions that you had to answer were, in the first place, the many questions. But the most important one was, if you push the button, did it detonate? And number two, was the yield as selected, as expected? And the obvious, or most people understand why the first question is important.
Right.
The second one is a little subtler because the answer to that question is important to the warfighter, because typically you target something, you want to make sure that the destruction is effective, and that depends on the yield. And if the yield is off, for example, if it's a fraction of what you thought it was, oops, then you have to send another one. So they cared about those kinds of questions. And then, of course, the other questions were the detailed questions about, okay, so what does the debris look like? You go into the field, you might actually know something about that. I'm not going to ask you. You do detailed forensics on the debris. You have recordings of during the explosion, of the neutron fluxes, gamma ray fluxes, all that stuff. And you use that to basically see whether or not things worked as you expected. So they knew that that program was very likely to come to an end. And of course it did. It did ultimately come to an end at the end of the 80s, early 90s, because the United States, although the United States Senate never ratified Test Ban Treaty, we were signatories to the treaty, and we behaved as if the Senate had ratified it. So we stopped testing.
So now we couldn't take a weapon out, stick it in the ground, and see if it worked and see if the yield was what it was. So then the question becomes, what do we do? How do we answer these questions?
So actually, the labs had an answer to that before the treaty was negotiated, because everyone knew that that question would be asked. What are you going to do? And the answer was, we are going to create a science-based program where we do two things. First of all, we do research as part of the science program to better understand how the weapons worked. The weapons as built were not just a science achievement, but also an engineering achievement, because there are certain parts of the physics of these weapons that were engineered and not understood from first principles. And that's still to some extent true. So if you no longer going to test and you no longer have the ability to actually find out during a yield experiment what could possibly go wrong, and if on top of that, for various interesting psychological reasons, that's my interpretation, we never really tested to failure. That was never done.
So what does testing to failure mean?
It means finding what the threshold is at which the weapon will not detonate. You want to know what's commonly referred to in the business as the cliff. You want to know, where is the cliff? At what point does the weapon not work? What would need to fail for the weapon not to work?
Okay.
And for reasons you can well imagine, you don't win many prizes for getting a weapon not to work.
Right.
It's one of those things. So it's interesting that all the tests were always successful.
Yes, they were. So explain what NIF is, like how it works, because it's quite spectacular that it works in the first place.
Yep. it is. So the idea of building something like that is a pretty old one. And it rests on the fact that there is a relationship between how a weapon works and how you might get something to ignite based on what happens at NIF. And I'm going to describe that for you. Okay. So what happens at NIF? So the idea is that you take a capsule that's filled with two isotopes of hydrogen, deuterium and tritium. Deuterium is a proton and neutron. Tritium is a proton and two neutrons. The isotopes of hydrogen, chemically they act just like hydrogen, but from the nuclear perspective, they're quite different. Why would you choose those two things? Because the neutrons are glue particles. They lower the threshold at which you can get the two protons to approach each other and join. It's a crucial point. The sun does it in a different way. The sun starts with individual protons. It sticks first two together, and then another two together, and those two, they ultimately stick together, and then there's a transformation, and all of a sudden you get helium. The helium nucleus, an alpha particle, has two protons and two neutrons, and what you know just from that result is that there's some very interesting nuclear physics that happened because somehow two of the protons managed to transmute. Kind of interesting.
It is. It is. And that's the astrophysics part, right?
That's the astrophysics or nuclear physics. You're right. Sometimes you can't tell the difference between those two. Yeah, it's very cool because, in fact, from the point of view of astrophysics, what's really great about the transmutation is that as part of the transmutation, that series of reactions releases a bunch of neutrinos. And those neutrinos have this great property that they can travel straight through the sun. Very few of them get scattered and disappear. Almost all of them come out. And that means we can detect them here. And so the neutrinos are a way of us looking directly into the interior, the center of the sun. How cool is that?
That's pretty cool.
That's pretty cool. And that's how we know, for example, what the reactions are that happens in the center of the sun.
Okay, what's the advantage of the sun?
Well, it has this enormous amount of gravity that holds the whole thing together. Because the temperature of the stuff is very high. Why is it high? Because two protons don't like to be next to each other.
Okay.
They have the same charge, they repel. And so you got to push them together. The way you push them together, you make them really hot, really fast. And if they're really fast, they can't come close enough, especially if there are neutrons around, to stick.
And so that sticking is fusion.
That sticking is fusion. It takes another force of nature, which we don't directly feel, but at those scales is felt, at those small scales is felt. And that's a strong force, a strong nuclear force.
So is there a way for us to make a sun on Earth?
So if the question is, have we ever done fusion before on Earth? Of course we've done it. We've done it since 1952.
Right. But have we done controlled fusion?
Ah, right. In the lab.
So that's a little harder, right?
In the lab, there's a bit of a problem there.
So yeah, can we make a controlled sun?
So the idea is pretty straightforward. So what you do, you take a little capsule and you fill it with deuterium and tritium, and exactly in what form I will talk about a bit later. But let's just say at this point that the capsule is filled with this stuff. And what you need to do is you need to compress it because there is a criterion called the Lawson criterion that tells you basically the conditions that have to be met in order for the fuel, which is this mix of deuterium and tritium, to ignite. And the Lawson criterion is a combination of sufficiently high temperature and sufficiently high density. And if you think about why you need both of them, I told you the answer to one of those. You need high enough temperature in order to get the protons to get close enough to stick.
Okay.
Why the density? Because you want this to happen often enough that enough energy is released that the plasma keeps replicating its conditions. If you don't have enough density, then the frequency at which two protons approach each other is lower. The denser the plasma is, the more frequently protons will approach each other, and therefore you release sufficient energy. And the key here is you want to ignite this. It's sort of like lighting a fire. You don't just want to start the fire. You want the fire to keep going.
Right.
You want it to continue the burn. And that's the reason you need to satisfy both criteria: high enough temperature and high enough density. So here's the problem. Right at the outset, there's a very simple analogy that will reveal the real problem here doing this, which is take a balloon, take a small balloon, one that will fit inside your hands. You cup your hands and put a balloon inside, blown up, and then what you're going to do is you're going to try to squish it. And what you'll find out almost immediately is as you're squishing it, if you're not squishing it perfectly symmetrically, it's going to bulge out somewhere, and you're not going to be able to squish it. It's very hard to squish something perfectly symmetrically. And the amount of squishing that you need for this little pellet is a reduction in volume of a factor of about 1,000. That's a lot of squishing. And so the smallest defect on the surface of this ball, if you're squishing it, say by, I don't know how you want to squish it, there are all sorts of ways of squishing it, but the smallest defect, any kind of asymmetry is going to cause a problem. So early on, the idea was to bombard this pellet with things that can push on the capsule. And there are two ways you can do that. You can push on it with light, in a way that I'll describe in a moment, or you can push on it with beams of particles, typically heavy particles. So there's a long history of thinking about doing this with heavy particle beams. There, it's the momentum of the incoming particles that were pushed on the walls and try to compress this little ball. With light, the idea is a little different. What you do is you take that little capsule and you surround it with plastic, something that ablates when it's heated.
Okay.
And when the laser light comes in, it burns off the plastic. The plastic streams away from the capsule, and it's sort of like a rocket effect. The streaming away of the plastic is a Newton's laws operating, action and reaction. This stuff is coming off, boiling off, and it presses the capsule. And what I just described is called direct illumination, or direct drive. And it's something that the folks at the University of Rochester's laser lab have been pursuing for the last 20 years or so.
Okay. It's really cool. That sounds very cool.
Yeah, that's what they're trying to do. If we can talk, if you're interested, I can describe what the challenges are there. They have different challenges to Livermore. Livermore had a different idea. What they decided is that it's challenging, they recognize it's challenging to make the laser light very uniform. So what they decided to do is use a trick. What they did is they put that little ball inside of a little cylinder. A cylinder is it's of the order of about a centimeter in diameter, and a little bit longer than that in length. And the cylinder has two windows at the ends, and the inside of the cylinder is coated with gold.
Okay.
And there's a thread, which is actually, interestingly enough, a tube. Technology is amazing. The little sphere that contains the fuel, the hydrogen fuel, is suspended inside of that cylinder by a little thread, but the thread is hollow. In fact, when you put the little sphere inside, suspended with this little thread, the thread has a purpose aside from holding the ball in place. It's used to actually fuel the little ball.
Oh, I didn't know that the thread had a purpose.
Right, it's actually injected. And so now I'm going to tell you a little bit more about this. The way it actually works is the whole thing is actually cryogenic. It's very cold. And the hydrogen, this mixture of tritium and deuterium, flows through this little suspended tube into the ball. And since it's extremely cold, the gas deposits as an ice on the inside walls of the hollow ball.
Okay, hold on. I thought you said we needed this to be very hot for fusion to happen.
Yes, it will get hot
Okay.
very soon. But at the beginning, it's an ice on the inside of this sphere.
Okay.
Okay, so now the thing has been fueled, so this little capsule is now filled with this ice of hydrogen. And then what you do is you turn on the lasers, and 192 of them.
Hold on. But this little capsule, it's in this like massive container, right?
Well, where it's sitting in a huge sphere, and there's an arm that comes out on the side, roughly speaking, in the middle of the sphere, that holds this little cylinder right at the center of this gigantic sphere. The gigantic sphere is many meters in diameter. It's huge.
Yeah. So you have this like centimeter capsule in the middle of like a multiple meter diameter sphere. So this tiny little capsule in this massive sphere.
Right, correct. And on the outside of the sphere, there are ports, there are windows, and those windows are the exit apertures for the optical system that brings the light from the 192 lasers into the sphere.
So 192 lasers are focused on a centimeter capsule.
Right. So, well, they're not quite focused on the capsule. They're focused on the entrance aperture of the cylinder. The light from the lasers never hit our little sphere. What they hit is the inside of the cylinder.
Okay.
And why do you want to do that? Because when you do that, then 192 lasers now have to use some numbers and some units. You can ask yourself how much energy is delivered into this cylinder. The cylinder, by the way, has a German name. It's called a Hohlraum, which means an empty space.
Okay.
And the answer to the question, how much energy is put in, is a bit over 2 megajoules. That probably means something to you, but maybe not to your audience.
So what is that comparable to?
So a joule of energy delivered every second is called a watt.
Okay.
And we have lots of 100-watt bulbs. So 100-watt bulbs means every second this bulb is consuming 100 joules worth of energy.
Okay.
So this thing consumes a bit over 2 million joules, not every second, but in a tiny, tiny fraction of a second, of the order of less than a millisecond.
Okay, that's a lot.
That's a lot. That's a lot. Yes, it is. So what happens is there's an unbelievable, it is really unbelievable amount of energy that's put into this tiny little hollow cylinder that's about an inch long and less than a half an inch in diameter. Huge amount of energy. And all that energy is deposited on the inside walls. And what it does is vaporizes the gold and brings it at a temperature of about 1,000,000 degrees. Now, stuff that's at 1,000,000 degrees radiates like crazy,
Mm-hmm.
and it radiates dominantly at X-ray wavelengths. So the inside of that cylinder is now filled with very hot plasma, but most importantly, with extremely energetic X-rays. And those X-rays hit the surface of that little tiny sphere that contains the hydrogen fuel. And remember I said that what you're going to do is you're going to coat that sphere, little tiny sphere, with a plastic that ablates. And it's going to be ablating like crazy because these X-rays are hitting the surface. And so it's that ablation that compresses the little sphere. Now the key is, why you want to do it this way, is that in the cylinder, the illumination is amazingly uniform. That's the trick. So basically, the purpose of the cylinder is to create a radiation environment around the little sphere that's as uniform as you can get it. So the little sphere is really uniformly illuminated, not by laser light, but by the X-rays that are produced by the laser light.
Oh, how clever.
It is clever. Yes, it is.
And so I was always so impressed that they could shoot 192 lasers at this tiny little, sphere. But now I'm very impressed with how they do the compression. Yeah.
Right.
Yeah.
That's how the compression is done.
So in December, the announcement that was made was that NIF finally achieved ignition.
Right.
So what does that mean? What is so important about ignition?
So what happened was, well, it wasn't just ignition, it was ignition and sustained fusion.
Okay.
So just getting the fusion process to start, that's been done, aside from bombs, has been done in the lab for a long time.
Okay.
That's an old story, okay? The question is, can you arrange it so that the energy that's released as you fuse, that it can then continue the burn past the point at which you deposited the energy to start the burn. So if you like, in the fireplace analogy, I start the fire with a match. And now the question is, once the match goes out, will it continue to burn?
Ah.
So think of the lasers are the match. They provide the match. Then the fusion starts, and now the question is, will it sustain itself? You know, is enough energy released in the fusion, in this little capsule, to keep it going?
So you mentioned that it consumed a megajoule.
Well, 2 megajoules were in the shot.
So it consumed 2 megajoules worth of energy. So in December, did it actually give out more than 2 megajoules?
Yes, that's the point. The gain was 1.5.
So it
3
gave
megajoules came out. 3 megajoules, a little bit over. The approximate numbers, roughly 2, a little bit more than 3 came out. Yes. The gain was 1.5.
that was the big announcement.
Right.
Okay.
They finally got gain larger than 1. And it was actually a lot more than 1. It was 1.5. It was that's cool.
That is.
Super
That
cool.
is. So
Yes.
that's
Amazing.
the fusion. That's like the sustained fusion part.
Right.
What's ignition then?
Ignition is just to start it. You want to have the thing catch fire. When you withdraw the match, it may go out again. The question is, will it keep going? And it did.
Okay. Okay. It's making a lot more sense now. Because NIF was the National Ignition Facility. So the whole thing was just, they were talking about, we're going to get ignition, right?
Ignition. And they did.
That's going to happen.
Wow. It's so cool. Basically, what happened was what I described to you was the idea of how this works, right? The basic idea. And what I left out were all the complications that actually were not fully appreciated back when you were there in '09, or actually when NIF was being built. I think the number of complications was stunning in number and super challenging to deal with. So the thing that really impressed me when I heard the announcement was that they figured it all out. Because I can tell you that for a number of years, including the number of years when I was a consultant to the program, I was dubious whether they're going to be able to get there. And I would say most people were. There are some diehards that are just, we're going to do it. And the thing is that to get there required the interaction with a great number of very different kinds of folks. It required people that are expert in hydrodynamic plasma instabilities, folks that understood the lasers extremely well. It turns out there are 192 lasers during much of the run of NIF were not exactly doing the same thing.
Okay.
Okay, so the illumination of the cylinder was not perfectly uniform, which meant that the X-rays inside that cylinder were not exactly as uniform as they thought. There were issues about how to make that capsule as perfect as possible. That relates to the balloon example I talked about earlier. It turns out there were issues with all sorts of instabilities that have to do with exactly how the capsule is held inside the cylinder. It's amazing how many different things had to be just done just perfectly correctly. And on top of it, as you probably know, at Livermore, in the weapons program in general, there's a very close interplay between theory, simulations, and the actual experiments. You don't do an experiment just nilly-willy.
No.
What you do is you try out the experiment on the computer, if you like, first. You see what do you have to do to make sure this thing works? And one of the real triumphs here is that demonstrated that the codes that they developed for NIF, that they actually work. That is amazing.
And so that's good because then it tells them something about how they apply it to the weapons.
Yes, they're not the same codes. They're different codes, obviously.
But some of the assumptions are the same.
But yeah, a lot of the physics is very similar. Absolutely.
So what I'm hearing from you is that it's much harder to simulate a bomb than it is to actually just build one.
Yep. The people that built the first bomb in 51, 52, when they were building it, they had slide rules. They had like Marchand calculators. I mean, the electronic calculators there were substantially less able than your cell phone. Okay. But they did it.
They did it.
Succeeded. Yeah. Yeah. So the fact of the matter is you don't have to know all the physics to make the thing work. But if you're not able to go to the lab or to Nevada, strictly speaking, and blow things up and try things out, then all of a sudden you need to know more physics. You can't just guess. You can't do trial by error.
No.
You actually have to know what you're doing.
So we talked about what the announcement in December was. What wasn't it?
It was not an energy event. And let me be precise about what I mean.
Yes.
So during the time that actually you were there was an ignition campaign. And I remember, because I spent my visits to Livermore regularly as an advisor, I fully remember that Livermore was told by the Department of Energy, in particular the NNSA, they're given a reminder. Please remember that you're working for the weapons establishment. This is not an energy experiment. We're not doing inertial fusion for energy. We're doing it because we are trying to understand the physics of fusion and a few things associated with it that's relevant to the weapons program.
I distinctly remember that because I remember that day we went to lunch and we did a back of the envelope calculation and said, why would anyone think we're doing energy for this? Like, it's impossible.
Right, right. And you can also ask, the Department of Energy does have a fusion program. It's sitting in the Office of Science, in the OFES, the Office of Fusion Energy Sciences.
Okay.
And you can ask, where do they spend their money? And the answer is they spend it on magnetically confined fusion.
Yep.
Tokamaks, mostly.
And we've talked about that because we had an episode on ITER.
Right. So that's where the money went.
Okay, so why isn't this an energy shot? Or why wasn't it, even though a lot of people talked about it as being an energy shot? What is that back of the envelope calculation?
Well, let's look at it this way. Did we have any doubt that fusion generates energy? No, of course not. We've known that since the 1930s when physicists first figured out how the sun was powered. It works, okay? Now you want to do it on Earth as a power source? Well, we know what the problems are. The problems are the plasma is super hot, it's super unstable, it's extremely difficult to confine. Just ask the folks that are running the magnetically confined fusion experiments. And if you're going to do it in a pulsed way, which is what you would do with inertial fusion, then you have all sorts of other issues to worry about, including how often do you have to shoot and how are you going to extract the energy?
So one problem at a time. How many times would you have to shoot NIF to be able to produce energy for like a power plant usage?
About in excess of 10 hertz, in excess 10 times a second.
10 times a second. And how often is NIF able to shoot?
Once a day.
So we're kind of far apart in ability.
We're about 6 orders of magnitudes apart, yes.
Okay.
Yes.
So energy also needs to be cheap. How much does it cost for one shot at NIF?
Don't think of it that way. Think of it this way. We have a gain of 1.5, right?
Okay.
To megajoules in, 3 megajoules out. Now you can ask yourself, how much energy did you put into the lasers?
So that's not taken into account. Okay, I'll ask, how much energy did you put into the lasers?
About 300 to 400 megajoules.
That's substantially more.
Right. And that means the lasers are about a fraction of a percent efficient.
Okay. So while the announcement's exciting in one way, it's like you still have to bring people back down to earth and say, whoa, 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 this is not an energy source.
No. As a physicist, and you're a physicist, obviously, you never say never, right? I mean, only
Correct.
fools would say never.
And you never say always. Never say never, never say always.
No, yeah, absolutely. Exactly. Right. But what you do know is you have a long way to go. It's a technological roadmap that's very difficult to master. You have to get lasers. I mean, the lasers at NIF are never going to be able to do this. You have to invent a whole new kind of laser that can do this. You have to run them at over 10 hertz. Wow. At that power level. Pretty amazing. And so you have to increase the efficiency. 1% efficiency is not going to cut it.
No.
You have to get the gain well above 1.5 because you have to make up for the loss of efficiency in the lasers.
Yeah.
Right?
Yeah.
And then nobody has yet come up with a sensible way of then extracting the energy.
Right.
Another little problem. And let me cut to the quickie of why I gave that interview. Okay?
Yeah.
Because that's a different story here, which we haven't touched on yet. So one thing I said to my friends at the Bulletin, I said, we, all of us here, really value the fact that the present weapons program no longer tests weapons in Nevada. For us, that's incredibly important. Please, let's not test. The shot on December 5 was a demonstration that the science-based Stockpile Stewardship program actually is real, that it works. And therefore, more than anything else, it demonstrates that the decision to not test and then rely on science to basically do the work that was done by testing in Nevada, that actually worked out. We know how to do this. So it's super important.
Did NIF do what it was supposed to do, what it was built to do?
Yes. That's the point. That is the point.
And so we should be concentrating on that and not on what it wasn't designed to do and what it was never supposed to do.
Yes. And Marv Adams, during the press conference, was the only one who said in the end of his little talk exactly the right thing, which is this was an incredible demonstration that we know what we're doing, that we have an understanding of the physics sufficient so that our simulation codes correctly predict what happens in the experiment. They're verified and validated. Wow, that is just so huge. And what I said to my colleagues there, I said, the real danger here is that if you sell this whole thing as an energy experiment, and there will be people saying this is ridiculous. It's ridiculous to think of this as an energy experiment, just as we were discussing before. Livermore and DOE are going to be attacked for wasting a lot of money for the taxpayer on something that is ridiculous, instead of being lauded for something that was really great. That was my prediction. Lo and behold, the week after that, there is an article in Bloomberg News, you can look it up, and in the Atlantic Monthly, which relied on Bloomberg, that basically said this was just a case of, I'm going to paraphrase, I'm not going to use it, I don't remember the exact words, but something to the effect that this is just a money-hungry lab that isn't getting enough money, just looking for more of a handout, and that's why this thing was done.
Oh, okay.
Yeah. And the reason they said that is not because they're evil, but because they were fed this news and didn't realize that there's another story here, which is actually the real story of why this was done.
Which is so much more. Oh,
it actually made me pretty angry.
Yeah, because that NIF achieved ignition and worked is so much more impressive when you look at what they overcame.
Right. And why they were doing it.
Yeah, and I understood why they were doing it, but the way you explain the physics, it's so much more impressive. I mean, it's a scientific and engineering marvel that they were able to do it.
Yep. I'm so glad you use those words. There's both science and engineering in there. And it was just awesome. What they did was awesome.
It harkens back to the Manhattan Project, where I use those same words. It's a scientific and engineering marvel that all these people from different fields came together to build something that worked. But this is saving lives.
Yes. And it's telling the world we have sufficient knowledge of how we deal with our weapons. We have no need to test. We don't need to test.
And that is a win.
Yeah, it's a huge win. And one of the things that always bedevils nonproliferation is always, people like the Iranians saying, well, you do it, why can't we?
Absolutely, yeah.
And this is a really good reason why we shouldn't test.
So do you think now that we have NIF and we have proven it works, that we should stand down our testing site readiness?
I'll tell you, as far as I'm concerned, I don't know. Because I do know the kinds of questions that can now be answered, but I'm not privy to all the other questions. These weapons are complicated devices, and there are other facilities that test other aspects of the device. For example, DART at Los Alamos, which is a hydrodynamic test facility. So I don't think we've answered all the questions.
Right.
But what we've shown is that if we work at it, we know how to make something work like this. And that's the important point. That's the really important point. By the way, I should also say that there's another issue here, okay? One that I think sometimes even the Department of Energy forgets, even the NSA, which is not really forget, but it doesn't emphasize it, let me put it that way. These weapons are going to be around for a long time. Many of us wish that we could make them disappear. I think most people would just like to have them disappear, but they're not going to disappear. And so you can ask yourself, okay, so, in 50, 60, 100 years, you're still going to have these weapons around. And the folks that built them are going to be in the ground. I won't be around. Most of the folks at Livermore won't be around 100 years. No one there today will be around 100 years, right?
Right.
So who is going to take care of the weapons then? And oh, by the way, those people, whoever they might be, will never have tested a weapon. They will never have been in Nevada to blow anything up. So what do you hope they know? What you hope they understand the physics and the devices and how all these things work well enough to take care of them. And one of the really great things about NIF is that it is a facility that allows us to train those folks, the next generation.
Thank you for listening, and thanks to Bob for taking time out of his very busy schedule. Please leave us a rating or review on Apple Podcast or wherever you are able. Visit us at mynuclearlife.com for more information about our podcast. Until next time, I'm Shelly Lesher, and this has been My Nuclear Life.